So last night I did some more work on the bit manipulation data lab and made some progress. Got a lot accomplished. And that there's three floating point problems remaining, and basically I didn't want to do those last night. I was kind of brain dead. I did use AI to help me on one of these. We're going to labs data bits.c. My intuition was right on a lot of them. This is the one that I had it basically it did the implementation for me. This is my implementation up here, but it came out to be something like 100 and some odd operations. So it was correct, but it was just too many ops. And obviously, like, just looking at it, like, it's going to be quite a bit of operations doing it this way. And so after coming up with my own solution that was correct but not optimal, I went to AI and basically asked it what type of idea it would want to do here. And the first thing it did is basically it reads out the sign bit, and then it says, I'm going to and sign with the negation of X, or it's going to negate the sign and it with X. And so what this effectively has effect of is converting the value to be a magnitude minus the sign bit, obviously, to see how many bits you need to represent that value. And then it does this like binary search type thing where it goes through, computes all these B values, and then sums them up, and then adds a 1 at the end here for the sign bit. So, I mean, this is a solution that I wouldn't have come to myself without a lot of thought and effort. And I didn't really feel like putting in that much effort. Like, I did get a solution that was correct, used only the appropriate ops, but it just wasn't optimal. And I actually did like my solution, even though it looks really ugly, because doing it for 32 bits, you have 31 lines here. But basically what I did is I shifted the bit over and then shifted the bit back. And if that equals the same value that we started with, then that bit wasn't important. So we're demonstrating the importance of every single bit in the bit pattern. And if it's not important, if it can be recreated through an arithmetic shift right, then it's not important. So I thought that was it was a pleasing property that I exploited. And then these double negations kind of just made it, they're necessary for correctness. They made it to where it was a Boolean value, so either a 0 or 1, instead of being potentially greater than 1 in some situations. So yeah, that was my solution, the solution AI came up with. I feel like I understand the solution, but if you sat me down and said implement this, I could possibly get there in it would take me a long time. I would not immediately come to this. So I guess what I'm taking away from this particular problem, because I had to rely on AI so much, is that while I can think about these problems and solve them, to be really good at this, I would have to invest more time into becoming really good at bit manipulation operations, to be more performant, to find solutions that are more optimal. And it's just a level of time investment that I don't feel like I want to do, at least not right now. I don't think it's a high priority for me. So I'm going through a process of prioritizing my learning, and I think this is a really good exercise. I did everything else just using my own brain, but this last one, I was just depleted, and I could not figure out a solution here. And it's a pretty tough one to solve. Anyways, the floating point stuff. So this first one I read it last night. Basically, we're returning the bit. So all these take in, or sorry, this takes an unsigned integer and unsigned. Sorry. This one takes in and returns unsigned. This one takes in unsigned, returns an integer. This one takes an integer and returns an unsigned. So this first one, we're just manipulating the bit pattern as if it was a floating point number. And they'll do casting on their end to like convert to and from floats and do the assertions in the test suite. But this first one is basically just multiplying by 2. And the easy solution here is to just increase the exponent by 1. But I want to demonstrate, say we have 4 bits. So going from 0, 0, 0, 0, and we're just going to count up here. Actually, let's do 3 bits. It'd be a simpler, less bit patterns. So we got 0, oops, 1, 1, 0, 1, 1. Like that. Okay. Sorry, my nostrils are inflamed this morning. All right. So we have 8-bit patterns here. This is obviously going to map to e is equal to 0. But then we wanted to look at other things here. So this would be e to the 2 to the power of 3 minus 1 minus 1. And this needs to be in parentheses here. So 2 to the 3 minus 1 would be 2 to the 2 would be 4. Minus 1 would be 3. So 3 is the bias. So it'd be 1 minus 3. Should be 2? Negative 2? That doesn't seem right. So you have 8. Basically, it's shifting by... I think it's a negative. Negative 2 to the w minus 1, and then a whole thing minus 1. So that would be... I mean, I could check the book here for the float. But I'm pretty sure that's it. Let's go back here. Exponents. The exponent e weights the value by possibly negative power of 2. Okay, the k-bit exponent field encodes the exponent e. Okay. They don't give you the equation yet. Because it's a different... Okay, so it's k minus 1 minus 1. E minus bias. Okay, so all ones. This is going to be... what do they call it? Denormalized. E is equal to 0. All ones. This is going to be infinity nans up here. Now this is 1, 2, 3, 4, 5, 6 values, not including 0, which I think 3 go down and 3 go up, right? I think that's the encoding. So this would be -3. E is equal to -2. E is equal to -1. E is equal to 1. E is equal to 2. E is equal to 3. I think that's the encoding. To be honest, I'm not sure. Let's double check. Let's go back again. I'm surprised there's not an obvious equation in the chapter. All right. Yeah, here it is. So in the normal case, these are these example numbers, okay. I guess, I didn't do any of the practice problems, so that's why I'm kind of having to do this now. The smallest positive normalized value has a bit representation with a 1 and the least significant. Okay. Negative k minus 1 plus 2. I'm just going to Google for it because this book is not making it really obvious. Float exponent bias, which is like a diagram. Come on, stop it. Yeah, I mean that's what I was computing. So it'd be 2 to the 4 minus 1 in our case, because we have, we have 3 bits. So 2 to the 3 minus 1 minus 1. So that'd be 2 to the 3 minus 1. 2 squared would be 4. Minus 1 would be 3. Yeah. Okay. So that works out for 3. But it's not. Three is the bias. 1 becomes -2. So you take the actual exponent, you add the bias, and that gives you the binary representation. So if the exponent is -2, you add the bias, which is 3. Oh, that's right. And in this case, the positive has an extra. So we take out 0, we take out infinities, we take out the subnormals or denormals, and we're left with 2 positions on the bottom and 3 positions at the top. Okay. I think if we just add 1 to the exponent, since the unsigned is a 32-bit value. So here's going to be my game plan. We'll say read out exponent bits, add 1 to the exponent, write it back. I love it when that Vim just decides to reorder shit. Okay. So to read out the unsigned floats exponent bits, we need to take, we need to AND it with a specific value. And I'll use Python to calculate. Actually, you know what? I can use fshow here. So the first nibble, I want a 0 and 3 ones, which would be 7. Second nibble will be all ones, which would be F. Third nibble, I want 1, 1. So that'd be 8, 0, 0, 0, 0, 0. So the exponent should be all set. The sign should be 0. The fraction should be 0. Why did that not work? Make. There we go. Sign is 0, exponent's all F, fraction is 0. Okay. So with that value, so that's also known as positive infinity. But we'll go over here and we'll say const unsigned is equal to that value. And we'll give it a name, call it positive infinity. So here we're going to say AND with the positive infinity, and now we'll read out our exponent bits. This will be integer exponent bits. Okay, and once we have that, we can right shift that. Actually, we can make this a char, an unsigned char. Exponent bits is equal to this thing, and then we're gonna right shift this thing out. Oops. So we have 8 bits, 9 bits, so it's gonna be 32 minus 9 that we have to shift out. Which would be 723. So it's going to give us our exponent. And I'm just going to printf that out, %d here. Sorry, %x. And we're going to give exponent bits here. And return 0. Okay. So now I'm going to run btest. This is going to be testing the float scale 2. The input is going to be the same value that we had for our little test here, which would be this. And that gave us out ff, which is what we wanted. Now, if we decide to set a bit 0, like say we put the 8 to 0, that removes a bit. So that should come out as FE. Yep. And then say I want to change, put this back to 8. Say I want to take this to E. That would be D, FD, I believe. Yeah. So that's reading out the exponent bits correctly. Cool. So I have the exponent bits. Now I can just say exponent bits +1. So now we've increased our exponent by 1. And now we put them back in. And so what we need to do is left shift that over by the same amount. And we need to store the result in a unsigned. So I'm going to left shift over. Actually, before I do that, I'm going to convert this whole thing into a unsigned value. Then I'm going to left shift over by 23. Okay, so now we have our unsigned with the bits correctly set in the exponent. So we need to OR this. So this would be expanded exponent bits. We'll call it like that. Unsigned. Okay. So how do we compose our new value? It'll be basically we need to zero out the values that are in the original value. So UF, and we need to zero that out with positive infinity. So wherever there's a bit set in positive infinity, we want that to be a 0. So I think we got to do like an XOR maybe. So an AND would read those bits, an OR would set the bits, an XOR if you have a bit mask of 01110 and you want to set the bits in X to 0 where they are set to 1 in the mask, but read the other bits that are 0 in the mask. How do you do that with binary, or say bitwise operators in C? So you have to negate the mask and then AND it. Okay. So our UF, we're going to then say, hey, negate mask and that together. So that, yeah, that makes sense that you would do that. Okay. And the mask is going to be our positive infinity. Okay, and then this whole thing we then OR with our expanded exponent. And that should be our result. Let's go ahead and make, and we'll run it. Okay, it ran for my test. It failed. So what's going on here? Let's look at the test case value. So that's with a sign bit set, but all exponents. Oh, so you need to negate the sign too. Right? No. You only have to negate the sign if you are transitioning from 0 to 1. Or from a negative exponent to a positive exponent, I guess. Okay. So here we got I guess if you are doubling in all cases, you're setting the sign bit to 1. Or sorry, setting the sign bit to 0, because any value times its times no, because it's times 2, not times itself. Okay, so why did this value 8? So 8 0 is just the sign bit set. So it's a negative 0, and we're saying multiply twice by itself. Well, let's just print out what it came out with. It says that it did it correctly. Then why was the other test failing? Oh, so I need to give it 0 here. Okay, if everything's 0, So here we can say, I'm gonna call this updated exponent. Here we're gonna say if exponent bits is not equal to 0, then we do this. Otherwise, we just keep it equal to 0, right? I guess we don't need to do that initialization. Exponent bits is equal to 0, and our frac bits are also equal to 0. Then we don't want to update the exponent. We want to double exponent bits and frac bits are both 0. Then we just return UF here, which means that we can take this thing here, unsigned, just take it out of there. So now we just need to read out the frac bits, which are going to be bit masked off. So they're the last 23 bits. So you have 1 signed bit, 8 exponent bits, and 23 that's 24, 632, yeah. So here we're gonna say, hey, so 23 would be 4, 8, 12, 16. 20, and then 3 would be a 7 here. And then we call this thing what? Frac mask. I'm going to call this thing exponent mask. Okay. So now we have to read out the frac bits. Frac bits, and I'm gonna rename this thing too to be exp bits. There we go. So that's gonna read out and with the frac mask, and we just don't need to be bit shift that at all. This will be exponent bits. And then we're also going to have a unsigned char exponent value, which is the exponent bits shifted over by that much. This is actually going to be unsigned, not unsigned char, or same thing like that. Oops. And then this needs to be that with a semicolon. Okay. So we have our unsigned exponent bits and our fraction bits. We're just going to read both of those out. We shift over our exponent bits by 23, which will convert them into a value, exponent value. And then we say exponent value here is equal to 0, and frac bits is also equal to 0. Then we just return our original value. Otherwise, we say, hey, exponent value plus 1, convert that back into an unsigned, instead of an unsigned char, then bit shift it over 23, and that's our updated exponent. And then we say, hey, the original value, set exponent masks values to 0, and then set them equal to an updated mask, or updated exponent. So that should handle that edge case. Looks like it does, but I'm sure we got other edge cases here. Yeah. So it doesn't like it when we have the value 1. So it says the value 1 basically is the smallest denormal value, I guess you would say. So we need to figure out what to do with that. We can kind of handle some of that by saying, hey, if the exponent value is equal to that, but we don't have frac bits, maybe we just take that up here then, where we say, hey, like this, if frac bits is equal to 0, then we return. Otherwise, we got to handle these frac bits, which is to bit shift them over 1 to the left. Now we have to set our, so frac mask, we'll have to AND that with frac mask. So we take our frac bits, we shift it over 1, then we AND it with the frac mask. So now we have our updated frac. I'm going to call this bits. Updated exponent bits. Bits. I think since we're already updating the exponent bits, I think that'll implicitly, so we'll go from -2 to -2, but we'll also get the implicit 1 added. So I think we're safe here so long as we do this. Okay. So I'm going to just declare these then. So these are going to be updated, unsigned. And then we'll do the same thing over here. We'll just set them equal to 0 for now, just to get things compiling and happy. But what we want to do is basically updated frac bits are going to be equal to frac bits initially. Updated exponent bits will be able to be equal to exponent bits initially. Okay. I think that'll work. What did we have before we ran this? 1 gives 83609. So that didn't fix it. Okay. Oh, because I didn't add the frac bits here. Let's go ahead and read the sign bit out. So we'll have a sign mask here, which would just be a what would this be? 8 0 1 2 3 4 5 6. Okay, so now we can just say, hey, we have sign mask, unsigned sign bits is equal to, I guess you don't need these parentheses around here. Clean that up a little bit. UF and sign mask. Your sign's never going to change. There we go. Make. Okay, so it passed that one, but now we got this other one. No, it's the same one. Why is 8 set? I don't trust this thing. Printf %x, and we'll just say what, UF here. We'll give it UF. Make, oops, make. Okay, it's passing in 1. It gave us some like crazy value. Well, it went to 2, but it's set to 8. That's the weird thing. The sign bit got set. Is this correct sign mask? 1 2 3 4 5 6 7 8. That's correct. Sign mask 8. How did that 8 get in there? So sign mask ANDed with that, it'll only come out sign bits. Well, let's go ahead and print out everything here. Printf. Can I do like a, what does this say, 8? Make a .8, I think it is. Make, there we go. Okay. So I'm gonna do the same thing for all of these, except sign bits. Exponent bits, frac bits, make, run. Sign bits are 0, exponent bits, so we read everything out right. And then I'm going to copy 2 of these, throw them down here, and we're going to say, hey, your updated exponent bits and this is going to be updated frac bits. Okay, make. Okay. Oh. It wasn't the sign. I got confused here because I thought, because it's not padded fully here. So updated exponent bits 1 to 8. So 8 would be zero zero eight 80. 0080 would be what bits are set here. So 0 for that, and then you have 8 bits, all zeros, or 7 bits, all zeros. 1, 2, 3, 4, 5, 6, 7. Okay, so 1 did get added to that exponent, which should be fine. Oh, okay. I think I need to do this. But we could handle handle the case where we lose a bit. Still have to do that. Okay, so now that passes, but I'm sure there's other edge cases here. Okay, so that was with this value now, which is 7F, FF, FF. 1, 2, 3, 4, 5, 6, 7, 8. Okay, that makes sense that would be the next one. Let me clear that, just rerun it. So your sign bit is 0, exponent bits are all 0. We have these fractional bits. 1, 2, we need to fix this thing. Fractional bits. So length of the sign bits is gonna be like literally, it's like a 1 bit. So that's gonna be a 1. Exponent bits are gonna be 8. Fractional bits will be 23, so 24 would be the closest, I think. Because 24 has to be divisible by 4. So that'd be 6. And this 8 here would be what, 2? Yeah. 1, 2, 6 when I'm printing that up. And then Maybe we go back to here because I do like seeing that all the padding is correct. So you lose a bit here. I think that'll work. Bam. Okay, next test case. Okay, he's spewing stuff out, so let's disable our printf. And we might have it here. Okay, we have another failing test case, which is here. 1, 2, 3, 4. So no sign bit, all exponent bits. So is that our, yeah, it's our exponent mask. Okay. So these are the positive infinity cases. So what I think I'm going to do here is I'm going to say if exponent value is equal to, so you have 8 bits, it could be 255. We'll say 0xff is the maximum, then we just return UF. Did I not make? There we go. Okay, so that takes care of that. Hey, looks like I got it. Make. Look at that. And then if we do DLC bits.c, okay, we get some parse errors here. Undeclare, oh, because you have to declare everything up front. Forgot about that. I think I can just move this down here. And then we got an illegal cast here on 472. Okay. I don't think I needed that anyways. Okay, just rerun our test. Still works. Okay, cool. All right, next one. Float int2. Return bit level evaluation of expression int f. Return bit level equivalent of expression int f for floating point argument f. Wait a minute, what? Float to int. Return bit level equivalent expression int. I'm getting an unsigned. Argument is passed as unsigned int, but it is to be interpreted as the bit level representation of a single precision floating point value. Anything out of range, including the infinity, should return positive 0? What? What the hell? I don't even know what they're trying to do here. Return bit level equivalent. Oh, this would be doing the casting. So you're giving it an unsigned. It actually is a float. And it's saying, hey, give me the result of casting this to an int. Shit. It's a numerical conversion. What happens then? You take the whole number part. This is gonna suck. Yeah, because it's 2's complement. Yeah. Well, we could work with 2's complement. Leverage that we can work with 2's complement numbers. Our result is going to be 2's complement, so we'll just work in 2's complement. And effectively what is happening is we are taking the fractional part well, let's go ahead and read out the bits again. Okay. And we want to read out the exponent value. We don't need the shifted stuff. So this shifted thing can go away. And we probably don't need this, but we'll come back to it if we do. So we have this thing, it's a exponent value. So the actual value will be 2 to the power of exponent times 1 point frac. That's like the that's the normal form. Or fraction plus 1. Two to the power, and this is to the power, not x and XOR. 2 to the power of exponent times the fractional part plus 1. And the problem is here, lies in this, is that if the exponent is, if we go back up here, the exponent is biased. If the exponent is 0, that means that we are dealing with values less than 1. Very small values. So we just returned it signed 0, I believe. It depends on the rounding strategy. And I think it's round to 0 because, well, let's just do a Kling REPL here. Sorry. Yeah. Do Kling REPL, and I'm gonna say standard IO, and we're going to printf out something here. What is it gonna be? The decimal value of 0.1 double. We'll say double. And we convert that to an int. Sorry, float maybe? I think it's double by default, yeah. And if you go all the way up to 0.9, it's still going to 0. It truncates effectively. Now if you're at 1.9, it truncates down. If you're at negative 0.9, basically it just truncates. It truncates the fractional part. Okay, so we can handle a few cases here. Just understanding that. So let's go back down here. I'm going to copy this little map here for me, just so that I have it for reference. And boom, 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 boom. Two to the power of 0 is 1. So basically, if the exponent's true value, not its value, unbiased value, I guess this should be exponent value if it was biased. Exponent biased value There we go. We need to convert it to an unbiased value. I think it's 127, right? I think we have that over here. $127. So you subtract off the bias. And now any exponent that is less than 0, we just return 0. But it's signed version. So if exponent unbiased value is less than or equal to 0, because 0 would be to the power of 1, which would be 1. No, so it'd be less than 0 then. Because you need 2 to the power of negative 1 to be dealing with the half level. Because there's an implied 1 position there. So 2 to the power of 0 would be 1. 1 times 1 would be 1 point something. So we need to be less than 0 but not equal to 0. Equal to 0 is fine. We can just throw away the fractional part. Value is less than sorry, say negative 1 is x. It's less than 1, but it's greater than negative 1. Yeah. In which case, we just return our sign bit. Not of sign bits. So that'll turn the sign bit into a value, and you can multiply that times negative 1. If, we'll just do an if here, if sign bits, then return negative 0, otherwise, else return 0. Okay. So we're rounding to 0. Now, if the exponent is anything 0 above, we have to say 1 plus the fraction. No, we can't do the fraction. Trying to think of a way of getting the value out here. Let's make sure we're handling these cases correctly though. So make b test for the test float to int, and the value we're going to give it is just 0. Gives 2. How? You gotta print out all this stuff now. Make. Okay, I said if the exponent unbiased value is less than 0, it should be less than 0 because you subtract it off of. Oh, but we did it as an unsigned calculation. Shit. So the exponent biased value will always be unsigned. The bias itself can be unsigned, but this has to be signed. And we have to convert this to a signed. But that might not be a good idea, because I think that might trip up the test cases. Okay, so signed. Now we have, it's going to convert this to being, so I want this to be signed. So now we have exponent. Nah. Okay, that's where the tricky part is. I can't explicitly convert. Exponent bias. Take the exponent bits, bit shift them over, and can I just assign them into a char here? No. I think that'll still work. Say note. Okay. Now that should work. Okay. Let's go to the next test case, which is this value, which should be just our normal value. So we don't have our sign bit, we have exponent bits set, and we have fractional bits set. So we got 4, 5, 6, 7, 8. Actually, we just have 8. Well, we'll just test for those. We do that up here as a special case. this is just this value here. So before, give 2 should be 1. 7F. Okay. So we got 3. That seems wrong to me. One, 2, 3, 4. Yeah, so exponent bits are correct. Why is this? Did we handle our bit shift wrong? Let's launch Python. Oops, Python. And if we have the binary of 3F80, sorry, 0x. Python show binary representation with padded zeros for a single byte. Python 2.7. So this would be dot format, and here we do 0:08b. Yeah, it's only 7. Huh. Oh, because it's 3, I'm missing 1 bit. It should be 7F8. So 3F8 is missing a bit. So here, this is a special case for infinity. We need a special case for if fractional bits So the biased thing here would be 0, 0. And we'll say this is a d-norm. Okay. So we know that we're a normal value here. And in the case where we have a normal value, if our fraction if our fractional part, which would be frac bits, is equal to 0, then we return 1 here. And you can see that in the test case, it says should be 1. Okay, so we got that test case handled. Still have plenty more to go here. So 0 itself. So when 0 comes through here, the exponent bias value is 0 here. And this is where we have to handle the d-norm. So in this case, we say, hey, if your fractional bits are 0 and your d-norm value is 0. But it could be a negative 0. So we want to take our sign bit and we want to like basically return that. Value is plus minus 0. And if you go back up here, you can see where we returned, but we just returned it as is. So you should probably do that here as well. But we can't because we're converting it to integer. So no frac bits, it's a d-norm. And we have no fractional bits, so it's either positive or negative 0. But there is no negative 0 in integer space. So return 0. Yeah, that works. Otherwise, we have no exponent, we just have a fraction. In which case we're going to return 0 in that situation as well. So d-norm round to 0. All right, so now we got this case, which is where we have 1, 2, 3, 4. So that's going to be 1 in the exponent. So that's where we go down here. Okay, it's returning 1. Why is that 0? There should be implied. I'm confused here. So our exponent bits have, it's a value of 1 for the exponent. Two to the power of 1. But it's a biased value. We want the unbiased value. So where's our unbiased value here? Yeah, this guy here. Negative 126, that makes sense. And a fractional part of 1. I think what we need to do here is just go into the normal case. Here. We might need this, but I don't think we do. So we just say if exponent unbiased value is less than 0, then we just, and then we don't have to do the sign bits because there is no negative 0. Alright, that'll handle that case. Alright, next case is here. Test float to int, failed. Gives 2, should be 1. The bias value is 7f. The unbiased value, okay, we just returned 2 here. So this is where you actually have to do the math. Because this is a normal, we take the fractional part and we bit shift it based on the number of the exponent. Let's try it. Say frac. We bit shift to the right to remove We have frac bits, but we don't have frac value. And frac value has to be positive. It's a magnitude. So let's compute frac value. So frac value is equal to the frac bits, and because they're already aligned like that, we need to just put a 1. We'll say norm frac value is equal to the that, and with a constant where we put a 1 in front, which would be fuck, man. Uh, 0x 0 0 0 0 0 0 0 0. Okay, so this is gonna be 1 1, obviously 1 1 1. So that's 20 and a 1 here, but we only have 23, and these need to be f's anyways. 1 2 3 4 5 6. So that's 8 from 32, which is 24. So this needs to be a, instead of an f, it would be a 7. So frac bits, and with that, I think frac bits already has that being done to it, which is frac mask. Yeah, we already have that done. So frac bits are good. So we want to and it with that 1 bit set here. So these are going to be zeros, 1 2 3 4 5. The 7 becomes an 8. So that's, yeah. So frac bits, unsigned, unsigned here. This is going to come out as a unsigned. There we go. Frac bits. What is this use of undeclared identifier? Oh, because I'm still doing a partial down here? No. There we go. Typo. Okay, so that gives us our unsigned normal frac value. Yeah, we'll do this D. Okay. Wait a minute, that's wrong. Well, I guess it kind of is right. Three F8. So this is an exponent. Did we not add our 1 in? Oh, we ANDed it with that. We should have ORed it. So we got frac bits OR with that. My bad, my bad. Okay, so now we have this normalized frac value, and we have this unbiased value of 0. That doesn't seem right. So we need to right shift over this whole thing. Sorry, not 31. 23. Okay. I think that took care of a lot of cases. But we clearly have some remaining. So let's do this one first, obviously. So what's happening here? We get BF8, so some of the exponent bits are set. None of the fractional bits are set. So we get 7F. Yeah, that makes sense. So 7F is our exponent bias value. So everything but one bit set on that. That's a lot of bits. Exponent unbiased value. Okay, we subtract off the bias. We get out 0. Oh, did we just not get the sign bit? Okay, we didn't. We got the right value. We just didn't get the sign. So where's the sign at? Okay, it came in because it's a B. Okay. So we just need to multiply this whole thing times the sign. So this whole thing, I'll put it over here and say sine times that. So you have to figure out our sine from our sine mask. So sine is a integer equal to 1. And then we say if sine mask, sorry, not sine mask, sine bits, then, oops, then we set sine equal to -1. There we go. Next test case, please. Okay. So this is our new value to test. And 7 would be everything but the sign bit. F would be, so you get 7 bits, but not the 0th bit. That looks correct. The biased value would be FE. Yep, that's correct. Fractional 0. Unbiased value is 127. So why does it give 0? So it could be one of these two things. We'll say printf out here. We'll say puts. Okay. So it's a normal value. This seems weird. So we have a unbiased exponent of 127. So it's a very big number. But then it's returning 8 zeros. So that's that'd be the floating point representation of that would be negative 0. And it's T min on 2's complement. So it's either negative 0 or T min, which is negative 2 billion something. Yikes, 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 yikes. I don't like this. It has no sign bits set. So that means it is a positive number. So that means we're relying on it wrapping around. Shit. things are not easy. Some of them are. Some of them are dead easy, but some of them just get stuck on here. It might be this situation that they're looking for to return that. Let's read the description again. Anything out of range, including nano and infinity, should return that value. So I guess what you can say is that we have how many bits of precision? How many bits of precision do we have? We have 32 bits minus 1, so it's 31 bits. And then we're offset by 23 already. So we can go up by what? 8? Yeah, we can go up by 8. So I'm going to say if exponent unbiased value is less than 8, then we return, sorry, I'm going to grab both of these lines. Say value is too big. Wait a minute, less than 8 or greater than 8? I think this would be greater than 22, right? Well, let's go ahead and get the prints out here. Hey, look at that. It works. Because anything that's too small, if the exponent's too small, it just gets truncated down to 0, which is what we want. Anything that's too big, we say, hey, just return the sentinel value. Cool. So let's run our B test now without that. So we have one more test to go. I'm gonna run the DLC bits.c. 525. What is it? Parse error. This is where it wants all of its stuff declared up front. Okay. We'll just do this. This is expected bias value. Maybe if we just move this down along with the sign, and yeah. We'll move it down to its last declaration here. And I think that's the only place that sign is referenced. Yep. Cool. Maybe that'll fix it. Okay. Whew. That was a hard one. I was about to give up. Persistence. It's a key to being a good programmer. Just be persistent. Where other people turn away, I sit down and beat my head against the wall to get it done. All right, float power is 2. Return bit level equivalent of the expression 2.0 to the power, oh no, x ordered with x? No, it's raised to the power. 2.0 raised to the power x. For any 32-bit integer x. Okay. Well, let's start by isolating this. Float power 2. Return bit level equivalent of the expression 2.0 to the power of x the unsigned value that is returned should have an identical bit representation as a single precision floating point number 2.0 to the power of x. If the result is too small to be represented as a d-norm, return 0. If it's too large, return infinity. Legal operations, any integer, unsigned operations, including so-and-so. So when you think about it, 2.0 is represented numerically in binary as 10. Dot 0, 0, 0. The power of x would then be to shift this value left or right by that amount. So it'd be the same thing as shifting 1.0 So the normal case, the case that we're going to be doing most often, so this would already be represented as, I'll get the bits out. Sorry, excuse me. These bit masks might be useful. So we can't get a negative number. So signed bits will always be 0. So that's done. Because it's 2.0 to the power x. And even if x is negative, that represents a fractional positive number, not a negative number. So there's no way that x can influence the sign. So that's done. The exponent bits. So we start off with 2.0 with an exponent. We'll just say signed. This would be an integer exponent is equal to x. So if we do 2.0 to the power of, say, like 4, that's the same thing as saying one times 2 to the power of 4. So our fractional bits will remain 0 because that's implied 1. Our exponent bits will be equal to a biased version of the exponent. So the exponent is x. So then we have to do our bias change. So let's look for bias. So the bias is that. Let's pull this down here. Oops. So this would be x minus the bias. So exponent biased value. So we're basically flipping this around. If we want the biased value out, then we have to add it to the unbiased value. Plus x. And then that'll give us back out our exponent biased value as a signed char. And then we have to bit shift that over. So if we want a unsigned, sorry. We just say exponent bits here. Exponent bits are equal to the biased value. If we look this back up here, we need to shift over by 23. Oops. And we can never have fractional bits set unless we have like negative exponents. And I think they're saying that you can just round that to 0 here. Oh no, there are denorms. Okay, so I need to handle the denorm case. Okay, make there we go. That's what I meant to do. There we go. Make tired of seeing this. Arg test range. On line what? 332. So since sign bits is always going to be 0, we don't even need to have it here. We can just remove that. Here exponent bits is being set to this value, so we can just move that down here. And fractional bits currently is unset. There we go. So we got, I'm going to do float power 2 to 2. Wait a minute. Why does it say should be 0? Oh, because I have to do -1, 2 like that. Okay. Wait a minute, the fuck? Oh, because it's a float here. Let's convert this. I guess the exponent is, oh, because it's in hex. So if I do Python here, 0x81, yeah, then minus 127. Sorry. I'll give you 2. Yeah, okay. All right. So we got C0 instead of 40. So it's 1, 2, 3, 4, 5, 6, 7. Yep. So 40 versus C0. So the difference between, oops, run Python here. Binary C versus 4 is 1 bit difference there. We did 1, 1, 0, 0. Oh, we have to subtract the bias here. Because, wait a minute. If you have a biased value, you have to subtract the bias to get the unbiased value. And here we have a unbiased value. So you have to add the bias. Right? Because if I just did this, the 1 would be set. Let's do like a 3 here. All right, let's do a make. And let's get a few test cases in here. So like a 1, a 2, and a 3. So 1, 1, 2, 3, 4. So it's a right byte. 1, 2, 3, 4. So we have C0 versus 4, 0. And that's consistent. So why are we getting C0 out instead of, we have an extra 1 there. So X is 1. Our bias is 127, so we go Python hex of 128. Wait. I'm just printing it out here. Sorry, exponent bits. What's the delta between C1 and 4.1? 0x C1 minus 0x 4.1 is 128. If we just didn't do this and we just say, hey, you're just bit shift over. What would that do? Oh shit, man, this is so confusing. All right, I thought this is what I had to do, is add the bias back in. Clearly it's not working. I had these exponent bit things set. If I make this and run it on the test case for the exponent 3, and I read out the bytes here, it's C1 with an extra bit and 4.1 with an extra bit. So if we do Python and we say, hey, 0x C1, bit shift over 1, because you got one extra bit there, it's going to be 0, versus 4.1. And the delta between those two, so 386 minus 130 is 256. And if I look at the binary output of this, just the magnitude, not the bit shift version. Yeah, the bit shift version. So if I do binary of this and the binary of 4.1, it's just an extra bit set. You can see it's offset. It gets an extra bit set in the high order bit there. So we're adding a bias when we should be subtracting a bias. I think that's where we went wrong there. So now we got C2 out instead of 4.1. So let's run the same thing. So we're going to do 0x, what was this? How many? 1, 2, 3, yep. 1, 2, 3, yep. So C2, bit shift over 1. How is that even, what? Oh man, I just don't understand what's going on here, man. Oh, it's because X. No, it has to be added the bias. Let's just do X. Fuck the bias. We'll see what the output is. So 41 here. 1, 2. So here's where we get a little messy here. Because we have a bit shift over by 30, sorry, by 23. That's what we would expect. And this 41 thing, 130. So you have to add 127. Right? That should get us to 130. So let's try it again. 23. How is that even freaking mathematically possible? Three plus 127 bit shift over by 23. Oh, something's wrong here. C1. Yeah, the exponent bits are not set right. Oh, because of fucking char. Well, that should still work, right? But I want unsigned. That's probably what happened. It overflowed. Unsigned char. Bias values X plus the bias of 127. X is converted to unsigned. Okay, that should work. Jesus Christ. That was confusing as hell. There we go. Jesus Christ. Okay, our next test case that failed here, which is we pass it. Float power of 2. You can't go to that power of 2 that big. What are you talking about? That's a negative. I'm gonna say if X is negative, we just like one times 2 to the power of -1. 2 to the power of -1 would be 1/2. So I'm gonna say it's just we just return 0, right? What is the expected? Yeah. So here we'll have negative if X is less than 0. Well, it's never equal to 0 because 2 to the power of 0 would be 1. Well, we know less than 0 is definitely going to be return 0 here. So this one is 1, 2. So that's a very big value. See if we got our zeros right at least. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 8, F. This is 7, and I got 3. So it's a single bit off. Well, we are a single bit off. So X is a very big number. We add our bias to that big number. I'm confused because that number exceeds the amount of bits that we have available, right? Because that's 4, 8. Like we only have 8 bits available for the exponent. We can't handle a value this big. Like if I copy this here and do F show of that, so sine exponent is FF. Okay, so we're just saying infinity. It's such a big number, it's infinity. I can do that. I could just return infinity. Instead, what I'm doing is saying, hey, you're very close to infinity, but you don't actually hit it. So I think what we have to say is like too big if X is greater than let's see, what values can we represent here? So X can be 127. So if we put Python here, we're going to be adding 127. So that should be able to fit. 128. And then we convert that to X. Hex. So I would say anything at 128 or above. So if it's greater than 127, then we have to return infinity. And infinity, we already have the encoding here. All right, make, oh, sorry, B test. Hey, look at that. I didn't need these. I didn't have to handle D norms. I guess D norms handle themselves. So make B test, everything passes, and DLC bits.c. Oh, what's going on here? Bias, fractional bits isn't needed. You just need exponent bits. Parse error exponent bits, because that happened before then. Okay, well, we'll just move these up here. Make sure that runs, make sure that runs. Okay, we got all the points, and then there's a grading thing here. If we run that driver.pl, we got all the points, score, cool. Get, I can get out of here now. There were some other things here, like what? Data.pdf, what the frick is that? Let's go and do a commit here. So we go under, right here, make clean. rm.bash history. Finish float. Get LGA, LG1, LGA1. Whoa. Huh. All right. Cool. We're done with the labs. Let's go here. There's like a lab somewhere, right? Yep. All right, it's almost lunchtime here, so I'm gonna take a break here. Come back. I want to see what the C programming lab was, because that's somewhere. And then we'll continue on. I like to watch this lecture, so I might hop on while I eat lunch to watch the lecture, and then we'll do some reading. Cool. All right, I'm gonna go ahead and end the stream here, and I'll be back after lunch.